Thank you. Can you all hear me fine? Anyone? Okay, great. So hello, I'm Bo. Today I'll be talking about our recent measurements probing electronic and magnetic excitations in ruthenates with resonant inelastic X-ray scattering. So, so I think it's a very nice thing to give a talk to an audience with potentially a broad background because it kind of forces you to go back to the basics. So I'm a magnetism person, so having studied magnetism for many years, over the years, you tend to develop this mental picture of what a magnet will look like. For example, there's a square lattice. It will picture the magnetism just coming from interacting spins or little arrows with a pairwise interaction Hij. So having studied many of these materials, you can kind of just write down Hij without worrying about too much of the details. And this is usually the starting point for most people from magnetism. I'm pretty sure this is also true for experts in the audience as well. But if you think more carefully, these arrows don't just come for free. They don't just exist like electron spin, which is given to us, but rather it actually comes from solving a very complicated atomic problem or molecular problem. So usually these magnetic building blocks can be a transition metal ion sitting in an octahedral crystal field, or it can be a cluster of magnetic ions in a dimer or a tetrahedron or so on and so forth, right? And the problem of knowing where this moment comes from is actually very difficult because number one, you have a lot of energy scales. Even with just one single ion, you have Coulomb repulsion, you have Hund's coupling, you have spin-orbit coupling, and crystal electric field. And if your crystal electric field is of low symmetry, you have many terms that's allowed. And in the case of a cluster, you also have hopping between different orbitals. So this is a very difficult problem. And another reason why it's difficult is because you have a lot of states. So if you just consider 4 electrons, which I'll be talking a lot about today, sitting in 5D or 4D orbitals, you essentially have 210 states. This is basically a counting problem. And the number of states basically increase dramatically as you go to more sites. For example, if you have a dimer, you have over 100,000 states. So as you can imagine, solving this is quite complicated. In fact, this is how complicated the energy level diagram looks with just electron interaction and qubit crystal field. This is probably the simplest scenario you can think of. And this is actually important enough results it's given its own name. It's called Tanabe-Sugano diagram, which is probably familiar to chemists. All right. And then you may be wondering, given such a complicated energy level diagram, where do we even start? This is just a single ion. And what if you have interactions and so on and so forth? So fortunately, most condensed matter systems, you have a well separation of energy scales. Typically, the interaction is very weak. So you can just forget about most of the excited state and focus on the ground multiplets or maybe the first few excited multiplets. So the problem simplifies enormously. But the prerequisite for that is that you have to know where you are on this diagram. And you might think that this is 1950s physics. The theory, yes, it is. But experimentally, we are only able to probe such intra-atomic transitions quite recently, especially in 4D system I'm going to talk about today. So just a little bit of introduction about why I think 4D and 5D magnetism is interesting. So specifically, I'm thinking about 4D and 5D system that are strong Mott insulators. So its magnetism can be described more or less atomically. And this can happen, for example, in double perovskite or this antifluoride structure where the ions are very far from each other. All right. So the really unique thing about 4D and 5D system in contrast to 3D is the size of their spin-orbit coupling is actually very big. So as a consequence, their atomic state is no longer just a direct product between spin and orbital, but rather a so-called spin-orbit entangled state. This I'm going to explain now. So because I'm going to talk mostly about D4, so I will start with 4 electrons in 4D or 5D orbitals. And because it's sitting in an octahedral crystal field, it fills the surrounding anion. It will split into EG and T2G orbitals. And because these 4D and 5D systems and their orbitals are very extended, they fill the anion very strongly. So the splitting is big. It's 3 to 5 eV. So to first order approximation, we just forget about EG. So this actually already reduced the number of states from 210 to 15, so which is pretty good. And we can actually even simplify the problem further by arguing that, OK, because the electron repulsion is very strong, so we basically follow Hund's rule to fill in its energy levels. So we basically fill all the up spins first before filling the down spin. So at the end, you basically have this lowest Hund's multiplet. You have basically a 2 ampere spin, so it's S equals to 1. And depending on where this downspin is, you basically have orbital degeneracy of 3. So in the language of orbital angular momentum, you can rewrite it as effective orbital angular momentum of 1. All right, this is nice state. So this is probably the best we can do in simplifying our problem. But the nature doesn't really like that many degeneracy. So in the absence of spin-orbit coupling, what nature tends to do is to have a structural distortion called Young-Taylor distortion. Basically, in this case, it splits the orbital into a singlet and a doublet. So now you don't have any more orbital degeneracy, and you have basically just a spin degeneracy of 3, which is spin equal to 1. This is usually the starting point in most materials without spin-orbit coupling. But really what's interesting is when you actually consider spin-orbit coupling as a dominant energy scale, you again start with S equals to 1, L equal to 1. And then if you include this term, which is S dot L, I think any undergraduate student can tell you that if you couple two angular momenta of 1, you basically get total angular momenta of 0, 1, and 2, which is a singlet, a triplet, and quintet. So the important thing here is that the J equal to 0, which is the ground state, is a singlet, number 1, is non-degenerate, and it's non-magnetic. So I think this is really the most dramatic example of what spin-orbit coupling can do, at least on a single ion level. That is to completely kill the magnetism. So another more subtle point is clear if you look at wave function. So here, the wave function is a product between spin and orbital, whereas here, the wave function in any spin-orbit coupled system is spin-orbit entangled in the sense that you cannot write them as product. So a direct consequence of this spin-orbital entanglement is that because the orbital part always feels the lattice very strongly, it's very sensitive to lattice distortion. So as a consequence, your magnetism, when you have spin-orbit coupling, is always coupled to the lattice very strongly. And you may think, okay, this is a J equal to 0 state. It's non-magnetic. It's, what's so interesting about that? So interesting things happen when you put it in a lattice. So there are many things can happen already on the local level. First, you can have a local non-cubic distortion. And because of the spin-orbit entanglement and the fact that this, even though these are magnetic multiplets, they actually feel the lattice very strongly. As soon as you include, for example, a tetragonal distortion, you basically lift off a lot of degeneracies. So instead of a quintet and a triplet, you now only have doublet and singlets, as shown here. So this is still kind of easy because it's still a finite number of states. A more difficult effect to take into account, which kind of becomes popular recently, is so-called vibrionic effect. This is none other than just dynamic Young-Taylor effect. So the idea is the following. Instead of sitting in a static crystal field, your oxygen cage can also vibrate and have its own normal modes of vibration, which can be represented as harmonic oscillators. So consequently, basically accompanying each electronic level, you actually have an infinite ladder of vibrational states. And you can imagine turning on their coupling, and basically you get something that's neither electronic or phononic, and you get something really complicated. So this immediately becomes a problem with infinite number of states. This is difficult. But what we really care about is what happens when you have ions talking to each other, meaning that there is exchange interaction between them. So instead of being localized on each side, this spin orbit excitons, or this excited multiplet state, can actually move around. And this is basically predicted for a D4 ion in a square lattice with spin orbit coupling. So what happens is that you can see that instead of being flat, which is what you expect for a local system, the energy momentum dispersion relation actually achieves a minimum at the endpoint. So for scatters in the audience, this is nothing but the antiferromagnetic wave vector. This means that because of the exchange effect, the system has a tendency to have antiferromagnetic correlation. And you might be wondering what happens when you increase the exchange to be so big that the bottom of the dispersive band touches the ground state, or when you reduce the energy gap so that it touches. So the answer is not surprising in magnetic orders. But it's actually not a simple type of magnetic order because you don't have a spin to begin with. What happens is that now it's energetically favorable to actually make some of the excited state into the ground state. So mathematically, if you actually write this, this excited state as a bosonic mode, this is none other than basically Bose-Einstein condensation of your triplon. So the question is, we have so many things going on at the same time. How do we even start? So as I mentioned earlier, in condensed matter physics, there's usually a separation of energy scales. Suppose we only care about the effect of exchange, which is given by ZJ, to think about collective physics. So naively, you would think, okay, you start with some single ion level, And then when you turn on exchange, all this band, all this basically single ion level, basically disperses into a band. It basically acquires a finite thickness. An argument is if different multiplets are far from each other, they don't really talk. They can't be coupled by the exchange. So if we are in the limit A with this exchange, you only really need to consider ground state and the first excited triplet. So it's a singular triplet problem in the zeroth order approximation. However, the situation changes if you actually start to have lattice distortion. For example, if you have limit B and you turn on exchange, because now the tetragonal distortion basically splits the triplet into a doublet and into a singlet. The singlet is at a very high energy. So basically, the low energy physics is given by these three states. It's S equal to 1 problem. So you can see that depending on where you are on this energy level diagram, as I mentioned earlier, actually basically determines your low energy physics. So the first step is to understand this energy level diagram. And then we come to the important part is how do we study them? So the main problem with studying this DD transition or transition in the valence band is that they're not dipole allowed, at least in a central symmetric system. And also their energy is typically very high on the order of EV in transition metal system. So because they're optically not allowed, so optical spectroscopy like optical conductivity measurement don't really work that well. And because they're at such a high energy, neutron scattering don't work well. So it's only this technique that's being developed recently. When I say recently, I meant compared to the history of neutron scattering, that we can actually probe this intraatomic excitations directly. So the idea of RIXS, resonant inelastic X-ray scattering, is that instead of exciting the excitations within the valence band in one step, it actually excites it in two steps. So you basically come in with a photon whose energy is tuned to this absorption edge. This can be 2p or 3p, and this can be your d orbital. And then you first excite a core electron to the excited valence band, and then you basically have a core hole now, and you have an additional electron in the valence band. So something can happen, which is very complicated, and eventually another electron falls back. So effectively, you excite an electron within the valence band. And mathematically, this is basically captured by this second-order perturbation theory, and this is given a name called Kramers-Heisenberg equation. So I only want you to pay attention to two things. Number one, you now have two Ds, which are dipole transition operator. So basically, this means that this is no longer governed by a single photon process. It's a two-photon process. Another thing is that there's this intermediate state. So this is actually the hardest part to deal with. The reason is because in addition to your valence band physics, which is a low energy physics, which already is complicated enough, you now have a core hole, which is non-perturbative. So what we usually do is that we assume that the core hole is so short-lived, and once the electron is excited to the valence band, nothing really happens, or nothing really is fast enough to happen before another valence electron falls back. So this is so-called fast collision approximation. So mathematically, it is basically just equivalent to taking out the denominator, and then this summing over n becomes an identity. So this is called fast collision approximation. So this will be what I will use to model the data, some of the data. All right. So now we have a good technique to probe, electronic excitations in principle. So I think it's a good time to talk about RIXS instrumentation. So essentially, this is a scattering technique. So like any other scattering technique, you have to have a monochromator that selects your incident energy and a sample, and then you have to have an analyzer that selects your outgoing photon energy. So the most successful application of RIXS is to 5D system at the osmium, rhenium, iridium L edge, which is from 2p to 5D. So they're successful because these are in the hard X-ray regime. So being hard X-ray means that their wavelength is short. So basically, all this monochromator and analyzer, optics can be crystals, usually silicon or diamond. And then by having this very specialized, detector analyzer backscattering geometry, you can achieve a very good energy resolution about, tens of millieV. And coming from a background of neutron scattering, you might think that, why this is impressive. The reason is because you're actually selecting tens of millieV out of 10K eV. So this is less than 0.01% in terms of resolving power. And this is in contrast to neutron scattering, which is usually 10% or less. All right, this also explains why ruthenium, which is what I'll be focusing on today, is difficult. It's because the ruthenium edge is 2.8 keV, and the wavelength there is too long to be using this crystal optics efficiently. So you have to do some tricks with specialized optics to actually get a resolution down to even just 100 millieV. And currently, there's only one place on Earth that you can do this. This is at RIXS at DAISY. And given how competitive to apply beam time, so this is not an approach we take. We actually use a different edge called ruthenium M edge. Instead of exciting from 2p, you actually excite from 3p to 4d. And this is while in the soft X-ray regime, so where the gratings work beautifully. So all the monochromatic analyzer now are basically gratings. So the difference here is that you cannot use this backscattering geometry anymore. So the way to improve energy resolution is to have a huge detector arm, basically. And then, yeah, so what's the advantage? So the advantage is that here the energy resolution is better than our edge, but the disadvantage is that this is actually an extremely weak edge. So we have to count very long to get reasonable data. So going back to 5D, which is most extensively studied because hardware X-ray RIXS works well. So you can imagine there has been hundreds of studies just to trying to understand the local spin orbit multiplet structure. So one thing that came out of this many studies on different kind of compounds with different structures and different level of distortion is that this atomic-like spin orbit multiplet structure in 5D4 compound in particular is very, very robust. So if you look at this 2 RIXS spectrum as a function of intensity as a function of energy transfer, you can see a bunch of peaks. These are basically transition to different atomic multiplets. They are basically identical, but it's quite remarkable if you look at their structure. One is a cubic double perovskite, one is a monoclinic double perovskite. And yet, it seems that the structural distortion, local distortion, doesn't really matter. And in fact, you can actually model this with just a cubic model, including spin orbit coupling and Hund's coupling, and that's it. So the main, at least part of the reason why this is so robust is because the spin orbit coupling here is really big. It's actually a dominant energy scale. And given such a big energy scale, basically all the small perturbations don't matter. And also, if you look at this, is basically a measurement on single crystal as function of momentum. So this is a scattering technique. You can vary momentum transfer. And you can see there is a little bit of dispersion to this band, but it's almost non-existent. So I think the conclusion for 5D system, or at least 5D4 system, is that the local physics works very well. You can just use a simple cubic model to describe their spin orbit levels, and that's it. All right, the question is, what about 4D? So far there's been only 2 studies, calcium ruthenate and potassium ruthenium chloride on D4 system, that actually shows something like sharp atomic-like transition that you can actually model. So there are 2 other compounds, ruthenium dioxide and I think calcium ruthenate 327, that shows quite broad spectrum, which you can't even model. Yeah. Yeah. So this is basically elastic scattering. So anything like low energy phonon can contribute to elastic scattering or any. No, so I shouldn't put j equal to 0 there. Yeah, okay, great. So any other questions? Okay, good. So the question is, what about 4D? So fortunately, one of the compounds that has been studied, potassium ruthenium chloride, has an analog in 5D that has been studied very well, so we can compare them. So this is basically the RIXS spectrum for osmates and ruthenates with the same D4 structure. It's just minus 4D and minus 5D. You can see there the overall structure looks similar. You have one peak here, this is j equal to 0, one peak here, j equal to 1, this peak here, j equal to 2, or rather, j equal to 0 to j equal to 2 transition. And you also have the same structure here, and you have an excited Hund's multiplet that's here. There's another Hund's multiplet at high energy in the osmates that's not within this range. So, qualitatively, you have the same number of peaks, everything seems okay. But really, the difference is quantitative. So here, because of the large spin orbit coupling, the splitting between these peaks are very big. So the first peak occurs at 0.3 eV. Here, the first peak occurs at 60 millieV. So it's 5 times smaller. Actually, such a small gap also is reflected in the magnetic susceptibility. So in this material, because it's not magnetic, the ground state is not magnetic. So magnetically, at low temperature, is basically given by this Van Vleck susceptibility, which is flat. Only when you start to populate the first excited state, you start to see deviation. So the small gap in the ruthenate is basically reflected in the fact, in the observation that this flat region is a lot narrower. All right. So a small spin orbit coupling. This is not surprising. This is ruthenium. The atomic number is a lot smaller, so you would expect the spin orbit coupling to be smaller. But the question is, given such a small reduction, a small spin-orbit energy scale, how sensitive is this state to external perturbations, like structural distortion or exchange and so on? So this is the question we want to address, at least in the first part of the talk. So for that, we actually look at the double perovskite, whose iridium analog has been studied extensively. And we actually chose a distorted double perovskite. It's monoclinic, and the local symmetry, it doesn't really have any symmetry. There's inversion, and that's it. But if you actually look at the bond length and the bond angle, it's not too bad. It's almost ideal. There's one bond that's slightly shorter, and the ruthenium oxygen square is not that perfect, but that's okay. At least it doesn't matter for the iridium case. So the question is, how sensitive is the atomic multiplet structure in this compound to such a small distortion? All right, the ground state has been kind of suspected for 2 decades, which is the singlet ground state. So if you compare this LMRO, which is the name of the double perovskite, to the chloride, which is cubic, you can see that their susceptibility looks the same with the Van Vleck region at low temperature. All right, now we did RIXS, and we basically try to understand the full atomic multiplet structure. So this is basically a RIXS map of RIXS intensity as a function of energy transfer and incident energy. So one nice thing about RIXS is that you can actually tune the incident energy to resonate with different features. So the reason is because now you have an intermediate state. For example, if you want to excite electron within the EG orbital, in the intermediate states, the core electron has to reside in the T2G, whereas if you want to excite from T2G to EG, in the intermediate state, the core electron has to be in EG. So there are difference in resonance energy, which is difference in EI, basically reflects the difference in intermediate state. So this also allows you to tell which is intra-T2G, which is T2G, EG, and so on. All right. So let's just focus on the intra-T2G excitation, which is shown here. Again, you can see that now basically you can tell the difference between LH and MH. So here you can see it's a lot noisier, and this is so nice. So the reason is because the intensity here is really weak, and you can see this number of photons per second. Okay, good. So overall, the spectrum looks similar. You have 3 peaks, one here, 2 low energy peak, 2 low energy peak A and B, and a high energy peak C. All right, so the ground state can't be too far from this non-magnetic singlet state. But quantitatively, the RIXS spectrum in this compound is actually quite different. Number one, the ratio between the first peak and the second peak. So in the absence of structural distortion, their energy ratio is basically only determined by spin-orbit coupling. This is about 2.7. Here is about 5. So it's very different quantitatively. And also with a better resolution, we can actually see a splitting in B and C. The resolution here is about 35 millieV. So all this cannot be explained with just a cubic crystal field. So of course, we went to do a modeling. I will skip you all the details. So the important conclusion is that in order to explain, at least even semi-quantitatively, what we observe, namely the splitting and also the ratio between these 2 peaks, you have to include enough crystal field terms to break the degeneracy of all the 3 orbitals. So basically, in this compound, locally, it really feels the surrounding non-cubic crystal field quite strongly. So the dominant crystal field term is this tetragonal term, which kind of makes sense if you look at the bond length, this bond being kind of shorter than the other 2. And there's also splitting between the XZ and YZ orbital that comes from the fact that this square is not perfect. But the important thing is that the RIXS spectrum can actually see such a local distortion. So after determining all these local parameters, spin-orbit coupling, Hund's coupling, crystal field, so on and so forth, we can now say that okay, the ground state is a non-magnetic singlet, but instead of J equal to 0, it's actually JZ equal to 0 singlet. And the excited state is basically JZ equals to plus minus 1. That's originally split from basically this triplet state, you can see here. And their energy is 32 millieV and 36 millieV, which is very low. And the reason why they're actually split, even though they're time reversal partners, is because this is a non-Kramers ion. So the Kramers theorem, which guarantees that 2-fold degeneracy don't work. So when we see such a low energy, such a small energy, which is not too small, too big, we were wondering, can we actually see some physics beyond the single ion model at low energy? So for that, we actually basically did neutron scattering. So the good thing about neutron scattering is you can see the energy resolution is a lot better. And one nice thing about this time of flight inelastic neutron scattering is that you basically get a full energy momentum resolved map at one shot. Of course, the disadvantage of neutron scattering is that it only covers, say, 100 millieV, 200 millieV, and that's it. All right. And if you look at the 6K data, you can see something at around 40 millieV, which is the range that RIXS see a peak. That's okay. But it's actually not a simple just one peak. So there's a strong band at around 47 millieV. There's a weak band at 30 millieV. And both of these are magnetic because they decrease with Q. The intensity decreases with Q. All right. And none of these energies agree with our model. All right. Another thing is that if you actually warm up the sample to 300K, you can see that this band becomes really broad and it actually softens. So this is quite clear. If you actually do a cut along the vertical direction, you can see that clearly the peak softens and becomes broader. And so this is basically using a different EI, which provides better flux, although it kind of cuts out lower part of the spectrum. You can see that this peak really softens and broadens quite significantly. So this, in particular, cannot be explained by a single ion model. Which you wouldn't expect any change to the excitation spectrum without any change in the structure. We didn't see any change in structure, by the way. All right, so how do we explain this? So there are two possibilities, or two types of physics that could be relevant in this system that's beyond a single ion model. The first one is, of course, intersite exchange interaction. Actually, the importance of exchange was already seen from the susceptibility data, which has a large Q rise temperature, about 200K, actually. All right, so now to model the exchange, well, it's not that trivial because you have a lot of states. So the argument is, because of the large tetragonal distortion, which split this J=1 triplet into a really high energy singlet and low energy doublet, and everything else is at high energy. So you can basically say that, okay, for small exchange, you only need to focus on these three states, which is basically your S=1 problem. And now you can write down an exchange Hamiltonian, take into account this, S=1 degree of freedom. And the answer is we can actually find something that actually kind of captures the data, but the form of exchange has to be quite special. So you can see that this is your familiar Heisenberg term, and these, for people who are in the business of 4D and 5D systems, these are basically none other than your Kitaev gamma term, which is relevant, for example, in ruthenium chloride. And it turns out that this is the only way we can predict two flat bands that we see in our data. All right, and the exchange coupling is here. So if I actually take this exchange coupling and just plug in and calculate on mean field level what the susceptibility looks like, so it's a pleasant surprise that we find that it kind of matches the data exactly. But if you actually use the single ion model from RIXS and calculate what the single ion susceptibility looks like, it actually overshoots your data by quite a bit. So this kind of tells me that exchange might be relevant here. So another effect which I don't really have a model for is the vibronic effect. So the reason why I think it might be present is because, so in a vibronic model, instead of a pure electronic transition, now you have basically all kinds of transition between electronic state to electron hybridized with electronic state hybridized with phononic state, and so on. So basically, when you have finite energy resolution and that many transitions, the end result is that your peak become broader. So this is basically a simulation for potassium ruthenium chloride. You can see that compared to a purely electronic model, the vibronic model predicts much broader peaks. And you also have a large temperature dependence because you can change your spectrum by populating the phonon, a kind of more phonon-like state. And this kind of agree with potassium ruthenium chloride. So one of the important predictions they make is that is this J=2 peak and this Hund's multiply peak that's really broad. And it kind of is seeing our data. So that might also suggest that vibronic physics is also important in this material. Of course, to really model this, or rather to tell which one is important, you really kind of have to have a single crystal sample. Yeah. Oh yeah, right. So I kind of glossed that over. So this is kind of a biquadratic term. So what the term does is basically kind of shifts the band up and down to match the energy. So basically, this term alone kind of determines the relative ratio between these two bands, whereas the JQ kind of determines the overall position in this bands. Yeah. So and it's kind of not surprising. I mean, this term has been considered for this, but I wouldn't go into too much theoretical detail because I'm not a theorist. So okay, good. Okay, so no, if you have exchange, you might be wondering, what about excitonic magnetism? Condensation of the excited state and develop magnetic order. In this double perovskite, exchange clearly is too small to do that. But I would like to just point out that excitonic magnetism has been observed in this compound, calcium ruthenate, which is quite well-known compound. Instead of a double perovskite structure, it has a square lattice structure with a corner sharing bond. So this geometry basically increases your exchange a lot. And in fact, magnetic order has been observed at exactly the endpoint. And if you actually compare the RIXS spectrum, this is measured at the L edge with the coarser energy resolution, they actually look quite similar. So you have a big splitting between A1 and A2, and you also have a splitting between A3 and A4. But one thing that we see that they didn't see is that we actually see a splitting at A2, which reflects lower symmetry crystal fields than tetragonal, whereas these see just a broadening. So I think this splitting is also there, it's just the resolution don't allow them to see it. So this basically also highlights the advantage of M edge compared to L edge. So I would like to just also show this really nice inelastic neutron scattering data from calcium ruthenate, which really highlights that the magnetic order here is not conventional. So if you look at this dispersion, in particular at 2 points, the pi-pi point and the 0, 0 point, you can see that it's minimized at pi-pi and maximized at 0, 0. So this is actually really strange if you consider magnetic order, because now compared to the primitive kind of structural unit cell, which is this smaller square, the magnetic unit cell is larger. It's square 2 times larger. So both pi-pi and 0, 0 are zone centers. So you would imagine that in a simple antiferromagnet like this one, like cuprate, this thing will come down. It's just their intensity will be weak. But the fact that it's kind of maximized is kind of really strange. And this is, in fact, captured kind of by the calculation. This is what you expect for a simple ordered state. But actually, this spectrum is quite similar to the spin-orbit excitation dispersion in the uncondensed or the non-magnetic phase, where the pi-pi is minimized, the 0, 0 is maximized. So this basically just tells you that the magnetic order here is not conventional, and the excitation spectrum still remembers that it comes from a non-magnetic state. All right, so this, I think this is very nice. Of course, if you have large single crystal for the double perovskite, we would love to see the dispersion and hopefully drive kind of excitonic transition as well. All right, so I think at this point you are convinced that in the 4D case, because of the small spin orbit coupling, which push everything to lower energy, the system becomes a lot more sensitive to small perturbations. And just to, to have more fun, we decided to look at more kinds of perturbation. So for that, we, instead of considering a isolated octahedron, we actually consider a dimer in this so-called triple perovskite structure. So this is a structure which actually consists of this phase-sharing dimer that's actually very close to each other. It's about 2.5 angstrom from each other, the two ruthenium. So when you have such a short distance, you would imagine that the hopping between the orbitals become relevant. And this actually potentially will change your magnetism fundamentally if this becomes larger. So the question is, how large is this? So this has been, actually this class of material has been studied a lot in the case of iridates, and they actually know the hopping very well, which is huge. It's actually the dominant energy scale in such a geometry. So the question is, what about ruthenates, which has never been studied? And the reason why we actually choose this class of material, in addition to it being studied extensively in the case of iridates, is that it's actually a very versatile class of material. So if you actually look at, this is basically for the iridium dimer, this is for the ruthenium dimer, you can basically put any amion there, and which changes your local structure almost quasi-continuously. So in the case of BIMRO, we basically go from, once you go from indium to yttrium to lanthanum, which is the 3 compounds we study, you basically see that the bond changes by like about 2%. So this is a tiny change. But what's really strange is that the magnetic susceptibility, although indium and yttrium are similar, lanthanum is completely different. So the effective moment is much larger in the case of lanthanum than indium and yttrium, which tells you something's going on. But how to explain this? Is it relevant to the hopping, or what's actually causing this change? Before us, nobody really understands. Before I move on, okay, this dimer contains 7 electrons. Sorry, I forgot to highlight that point. Okay, good. So even before going to details about the BIMRO, I would like to just explain a little bit about what hopping can do in a magnetic system. So basically there can be 2 limits, so-called Heitler-London limit versus a molecular orbital limit, depending on the size of the hopping between the ions. So in a Heitler-London picture, the hopping is much smaller than U, so the electron still likes to stay localized. So you can imagine that the atom still retains its atomic characteristic, and their spins kind of fluctuate more or less independently. And at low energy, it's basically controlled by this exchange coupling. Right? It's much smaller than either U or T. Right? Whereas in the molecular orbital picture, you can imagine that when T overwhelms U, what happens is that basically these orbitals will hybridize to form molecular orbitals. And you have to fill in these molecular orbital levels as if you're doing the same for the atom. So the question is, how do we tell them apart? So here, it's a non-magnetic singlet. Here, once you include exchange interaction, it's also non-magnetic singlet. So bulk susceptibility, if this J is large, you can't really tell. So RIXS has been quite useful to distinguishing between these two limits, at least in case of 5D dimer systems. So there has been a lot of studies on this class of material, so I'm just kind of highlighting two that I think is quite nice. So the first one is on this 5D5 dimer, which has a single hole on each iridium site. And I think it's a very nice study because it actually tries to go from the localized limit to the dimer limit by diluting the iridium site. So in this limit, which basically substitute most of the iridium with titanium, so you basically only almost have isolated octahedra, where on this limit, every iridium is in a dimer. And you can see that RIXS spectrum just look totally different. So in the case of a single hole or isolated iridium 4+, the RIXS spectrum is actually simple to understand. This is basically the same as all other 5D5 compound. You basically have a peak at about 0.6, which is the spin orbit coupling energy scale, and we have a splitting between them because of the trigonal crystal field distortion. On the other hand, if you think about this single ion picture, at most you can have 2 transitions, and that's it. But in the dimer limit, you can see that you have a lot more than 2 transitions, at least 3. So this basically tells you that this picture cannot work. So you can actually quantitatively explain this by having a molecular orbital formed between these 2 sites. This is just a schematic. The real physics is a lot more complicated than this because of the correlation effect and all that sort of things. But I just want to point out the really striking difference between these 2 limits. Also, the same thing is observed in, for example, 5D4. And in the single ion limit, if you remember, you have 2 peaks corresponding to J equals 1 and J equals 2. And you have a lot more peaks when you have a dimer. So this all tells you that you cannot think of these clusters, at least in the 5D limit, when the hopping is big, as isolated transition metal ions. In other words, the molecular orbital picture is the correct picture for the 5D. So what about 4D? All right, so we basically did RIXS measurements on 3 compounds. Although you can see there's just a lot of very little data, but actually each of these scans takes more than 10 hours. So it's not easy measurements. So this is basically the same RIXS map that I showed you earlier as a function of this energy transfer. This is instant energy. You have a number of blobs. This is intra-T2G. This is a T2G-EG. The more excited blob is transition from the T2G orbital to the surrounding ligand, and the D is from the EG orbital to the to the ligands. So this is not important. So the important thing is really the intra-T2G excitations, which is shown in C. So if you compare indium, yttrium, and lanthanum, remember that their bond length changes by less than 1% when you go from one to the other. Indium and yttrium, they're similar, and their magnetic susceptibility also looks similar. That's OK. But the RIXS spectrum is completely different from the lanthanum case. If you look at the energy scale, which is affected, it's the spectrum weight below 1 eV is gone in the lanthanum case, but it's there in the indium and yttrium case. So it's very striking that how such a small change in bond length can actually affect the physics at such a low energy, at such a high energy. All right. So this is one thing that we don't understand. Another thing that we don't understand is actually just how do we even explain the spectrum in lanthanum. So the reason why we think it's confusing to begin with is the following. Because we started with a kind of a localized limit. So if you think about what happens if you start with a localized limit, you have 7 electrons on the dimer. So you have a T2G3 side and T2G4 side. So you know what the spectrum looks like in the T2G4 side. You have a low energy spin orbit multiplets. So there are transition amongst them. And there's also excited Hund's multiplet. You can have transition to that as well. In the T2G3 side, it's a little easier because you don't have orbital degeneracy. So S equals to 3/2, L equals to 0. You only have this excited Hund's multiplet. And you can sum them. You basically get what you expect for the localized limit. You have to have this low energy spectral weight that's very strong. And this spectral weight was indeed observed in the D4 double perovskite. All right? But the problem is that we don't see it in the lanthanum case. So this already tells us that this local limit cannot work. And we actually have tried to just perturb around this local limit. So this is basically the RIXS spectrum plotted as a color scale as a function of energy transfer and kind of perturbation, which we take trigonal distortion as the perturbation. And we do the calculation for no hopping or small hopping. And we see that because of the large separation between these two features, they can't mix. So basically, this low energy spectral weight will stay very robust. So our main goal at that time was really just trying to see whether we can even explain qualitatively the spectrum that we see in the lanthanum case. And it turns out the only way we can explain it is to have a large T1 to basically push up most of the spectral weight to high energies until it actually merges with this Hund's multiplets. So now the spectral weight here is small, right? And to our surprise, I think it's a very beautiful thing, is that once you are in this limit and you start to do perturbation on it, like changing trigonal distortion, now you can see that the RIXS spectrum actually sensitively depends on what size of the trigonal distortion is. In fact, at a very small trigonal distortion, you actually have a sudden change in the RIXS spectrum. And if you actually look at 1 and 2, it actually captures indium, yttrium, and lanthanum beautifully. And and then just to make sure that we understand the physics, we also did, using the parameters that we got from RIXS at 1 and 2, to calculate what the magnetic property looks like. And this is basically the ground G factor, which is the ground state magnetic moment as function of trigonal distortion. You can see that there is a sharp jump here, all right, which is coincides with this sharp change in the RIXS spectrum. And this actually is very nicely agreeing with the fact that lanthanum has a bigger moment. And we also did the same thing for over the entire temperature range, taking into account thermal population. Again, you can see that the lanthanum regime does have a much larger moment than the indium and yttrium regime. So we think we understand the problem. How do we explain the magnetism in this dimer system, and what's the relevance of T? And we believe that the change in the lanthanum and yttrium is because of trigonal distortion. But really the fundamental question is, why such a small bond length can drive such a change? So this change happens because the excited state starts to cross the ground state and you have a transition. So why is this dimer electronic state so fragile? So for that, we basically plotted it. This is the energy level diagram on top of the RIXS spectrum as a function of T1. So this is just varying T1 without trigonal distortion or anything. You can see that at low T1 limit, so localized limit, the first excited state occurs at 0.1 eV. So it's kind of big. Once you turn on this T1, you basically start to have a lot of density of states at low energy. So all these states can potentially cross the ground state to give rise to this transition. So basically, energetically, the fragility of this electronic state here comes from the large density of states. So that's OK. And another thing is that you can see one of the states actually comes from this excited spin orbit excited state. So in the non-interact, or rather decoupled limit, so this state basically is when the T2G4 side is in the J=1 state. All right. So also, what's the relevance of this particular yellow line? So this we can try to gain more understanding by doing calculations. So first, I'm just going to tell the conclusion. The reason why there is so many density of states at low energy is because of a unique kind of combination of energy scale in this dimer, a large hopping and a small spin orbit coupling. I'm going to go through them one by one. So if you actually just fix spin orbit coupling and vary hopping, so this is T1 equals 0.5, 0.75, which is what we use, and 0.95, which is even larger. And then sitting at each of this limit and kind of do perturbation on it, you can see that this transition only appears here, going to lower and lower trigonal distortion at the limit of large T1. So this tells you that T1 is important to actually push this states down and to increase the density of states. And what about spin orbit coupling? So for fun, we basically set the spin orbit coupling to be 0.4, which is what you get for iridates. And then do the same calculation. And you can see that, OK, when we vary T1, yes, basically, you can see that this peak starts off at 0.3 and 0.6. This is the energy you observe in iridates. And then when you turn on T1, you can see that this first excited state kind of stays almost above 0.3. And then if you are in the large T1 limit and you do a perturbation, you don't see the transition. So I think we understand why this dimer is so fragile is because you have a small spin orbit coupling, which makes the 4D system inherently sensitive to perturbation. And now you add a T1, which actually makes the system very unstable. So you might be wondering, can we actually drive quantum phase transitions in these materials? It turns out that we can. Actually, this is the work done by Chang. And we also got the sample from Chang, actually. So in fact, he did neutron diffraction under pressure. So this BLRO component actually magnetic orders at around 25K. And you can see that by applying a very small pressure, it basically kills magnetic order. So whether this is actually due to a global suppression of magnetic order, actually due to a suppression of the local moment, as suggested by RIXS, this we have to do RIXS under pressure, which is kind of difficult. So in conclusion, I hope that you now appreciate just how interesting the physics of 4D is, because how sensitive their local multiplet levels are to perturbations. So these actually make them really beautiful system to study quantum phase transitions, for example, with external perturbations. But the more important thing, as an experimentalist, what I learned from this work is that MH is actually very powerful too to actually study 4D system. So with that, I'm happy to take questions. Yeah.
You talked about 5D system,
Yeah.
4D system.
Yeah.
Is there an equivalent 3D system where you turn off the spin orbit plane? Can you make contact with that?
Yeah, I don't know which so molybdenum is D1. I don't know what's the elements above ruthenium. Do you know? Iron. Oh, there you go. Iron. But iron, I think orbital also plays kind of, and also you don't have D4 ion, do you? No. Yeah. Okay. Yeah. Okay. Yeah. Yeah. Right. Because there's. Yeah. The T2G splitting. T2G is too big. Yeah, for the 3D, the T2G splitting is smaller, so that you basically populate EG first before going to the T2G. Yeah. Right. Yeah. Yeah, so basically it'll be really soft X-ray, L edge, and it'll be really strong. So it's easy to do. Yeah. Yes. Yeah. Oh, so. Oh, I see. Mhm. Oh, so the. Yeah, right. So so this is effective moment, not susceptibility. Huh? No, but actually I think you're thinking of more like what is it called? It's kind of Hitler-London picture. You have kind of coupled singlet and then a coupled spins, and then as you cool down, you start to develop a singlet state. So here we're really talking about kind of a molecular orbital type physics, where you can't really think in terms of coupled spins. So the excited state, even though I showed this, I don't even know what these excited states are. It's just carries some angular momentum. Yeah, so basically it's kind of, you can see that if you start from here, and this is tens of milli EVs, you really have to work out all the. Yeah, right. Yeah, so basically I think the main message here is that even in this dimer system, oops. Yes. Okay, so because you have an even odd number of electrons, so the ground state is definitely magnetic. So the ordering is actually basically ordering of, you can basically this whole thing become one magnetic and carry some pseudospin 1/2. And ordering is actually the ordering of pseudospin on the dimer. So it's kind of ordering of molecular moment. Yeah.
You're saying that there's only one instrument that can do.
Yes. Yeah, right. It's in DAISY. It's actually built by Leonard, Yongjun's former student. Yeah, yeah.
So it's the difficulty.
No, I mean they still use a crystal monochromator and analyzer, but it's very off speculate, in some weird geometry that you have to kind of work out carefully to optimize the resolution. So you have to select carefully what crystal you use, number one, and you have to design your instrument such that it really optimizes your resolution. So even with such careful design, the resolution there is, as you see, 160 millieV, which is not impressive. Yeah. It is the best in the world because there's only one in the world. Yeah.